Now we're going to move on to our next panel, and I'd love to introduce Professor Rosario-Ortiz. Professor Rosario-Ortiz is a professor in the Department of Civil, Environmental, and Architectural Engineering at University of Colorado at Boulder, specializing in wastewater reuse, advanced oxidation processes, and water treatment, as well as natural organic matter and environmental photochemistry. He holds a bachelor's from University of Puerto Rico, so a fellow Caribbean, and also a master's from the California Institute of Technology, and a doctorate in environmental science from UCLA. He also serves as an executive and associate editor for environmental science and technology, and has held multiple leadership roles in the American Waterworks Association. So with that, Fernando, thank you so much for being part of this summit, and we're really looking forward to your panel.
Thank you very much, Adelina, and thanks everyone for joining us today. Again, my name is Fernando Rosario from the University of Colorado Boulder. Our second panel is going to be focusing on contaminant identification and reduction, specifically around advanced methods, and a discussion around how do we move forward when it comes to contaminants in water. So next slide. As has been mentioned before, we're inspired by the United Nations Sustainable Development Goals. As it concerns to us, goal number 6 is around water, and target 6.3 essentially states that by 2030, we will improve water quality by reducing pollution, eliminating and minimizing release of chemicals and materials, and halving the proportion of untreated wastewater. As an indicators for this, we have proportion of domestic and industrial wastewaters that is safely treated, and proportion of bodies of water with good ambient water. As we think about organic contaminants, this obviously becomes a challenge, because it means that we need to understand what contaminants are there, and we also need to understand how to remove them. Next slide. I took this figure from the US EPA. When we think about contaminants in watersheds, in cities, in small communities, what have you, we always think about how the sources of contamination are numerous and varied. In this graphic here, we have a system where you can have a septic system from communities that are not attached to a centralized wastewater system. We have the effects of agriculture when it comes to pesticides and fertilizers, any abandoned wells, landfills, or other locations where pollution can be released from, and how that can impact then surface water. The concentrations of and types of these compounds can vary and depend on the source. Over the years, we see that we can almost kind of tell what kind of activity you have if we look at certain indicator chemicals in the water. When we think about in terms of analytical chemistry, for example, or environmental engineering, full accountability of all these sources of and contaminants is challenging. We have many sources, especially as you go to medium and large cities, where you can now have runoff from streets and industrial operations and all kinds of things. And we have an ever-evolving need for better analytical approaches and removal strategies. Next slide. In terms of potable water production, we always teach this as we teach these classes, right? Potable water systems, drinking water systems, originally were designed for minimizing acute risk. One of the greatest public health achievements was essentially the ability to treat water and reduce waterborne diseases in the general population. For organic contaminants, we think about it, but the processes were not quite designed for removal of organic compounds. So we need to consider what processes can we add to a potable water system, for example. And as one of our speakers is going to talk about, also how do we do this in a wastewater setting. One of the things that we see a lot of science and engineering being developed around these processes to remove organic compounds from water, but we also need to consider that we need processes that are robust and sustainable. We need processes that are easy to scalable to medium and large cities, but also so that small communities can run them without a significant added burden to the community. Next slide. From a global perspective, as we think about this beyond maybe United States, European thinking, we have a wide distribution of needs around potable water production and delivery. There's a wide distribution of economic capacity available to safeguard water supplies and guarantee safe drinking water. And we see this in many different places, right? In some places, we might be thinking about sub-PPT levels of contamination. In other places, we might be thinking about metal levels, metal contaminations from mining, or we might be thinking about erosion and how that impacts source waters. There's also a wide range of environmental regulations and local conditions that we need to consider. So in terms of how we think about it, this overall creates a challenge for chemists and engineers to achieve the goal of providing safe drinking water to all in a way that, again, can be sustainable and robust. Next slide. With that, I'll turn it over to our four speakers today. Our speakers are going to be Barbara Kasprzyk-Hordern from the University of Bath. Then we'll listen to Juliane Hollender from Eawag and ETH in Zurich, Susan Richardson from the University of South Carolina, and Mark Ralph, President and CEO of Axine Water. Next slide. I'll now hand it off to our first speaker, Barbara Kasprzyk-Hordern from the University of Bath. Barbara, take it away.
Thank you. And thank you for the opportunity to allow me to speak today. Could I have the next slide, please? So I decided to study chemistry all these years ago because I was really concerned about environmental deterioration caused by chemical pollution. And it is frustrating, surprising, disappointing to realize that all these years later, we still struggle with some of the persistent pollutants that I learned about when I was much younger. And there are many reasons for why this is. Obviously, we have technological issues, we have policy issues, societal concerns. But from a chemist point of view, we really struggle still with understanding very complex, ever-changing chemical mixtures that enter the environment. And we are also not so good with making associations between these ever-changing mixtures and ecological responses. So how, for example, aquatic organisms respond to chemical mixtures. And we also not very good with making links between or extrapolating, working across scales from molecular, genetic, through to organism and ecosystem level. And most of all, very frustrating for me, is that we still talk about the public health, and we also talk about environmental health. Actually, there is only one health. And we need to really change our mindset in order to be able to approach chemical pollution issue in a more holistic way. So over the last 20 years, I've been working very closely with many students and colleagues across the world and trying to develop a new tool that can enable this holistic understanding of environmental issues and public health issues, so One Health. And this tool is called, this approach is called water-based epidemiology. Could I have a next slide, please? So what is it about? Apologies for the very busy slides. So every moment of our life, we're exposed to various different stresses. There can be chemical stresses, such as hazardous chemicals, pesticides, and there can be biological stresses, such as pathogens. And our bodies respond to this exposure with the formation of various different entities. We call them biomarkers. They end up in urine, with urine and feces in wastewater, and with wastewater if untreated in the receiving environment. So what we do in the context of water-based immunology, and it's one particular dimension, WB wastewater-based immunology, we are looking for this tiny entity. So it's a needle in a haystack approach in wastewater, in trying to understand, obtain a fingerprint of both community environmental health. And we do it with the utilization of modern technologies such as mass spectrometry, as well as sequencing to enable us better understanding what's out there. And we applied this approach in various different scenarios, and you can see some of them on your left-hand side. I would like to mention only two of relevance to today's discussion. One is the presence of chemicals intended for human consumption, so pharmaceuticals in the environment, and significant issues when it comes down to environmental health, especially antibiotics, antimicrobial agents, and looking at environmental hotspots that are linked with antimicrobial resistance. The other group of chemicals we spend a lot of time investigating and we're really concerned about are the chemicals that actually originate in our households. They are in personal care products, they are in plastics, leaching from plastics, chemicals that are not intended for human consumption, but they find way into our bodies. and they trigger various responses. So these are, for example, plasticides. So we did a lot of work with bisphenols, PFAS, and various other chemicals. And one might ask a question, okay, so we have a problem. We have lots of different chemicals in our waters. What do we do about this? Could I have a next slide, please? We could do various things about this. And I think first thing that always comes to our mind, especially, you know, myself, I'm a chemist. We need to introduce new technology. And of course, we need definitely new technologies. Some of the advanced technologies are carbon thirsty. So we need to also kind of balance water quality versus climate change issues. We therefore, in our work, are looking into at source interventions, so more kind of aligning with One Health actions. What are they? We are looking into, for example, pharmaceutical stewardship. So we have observed that the prescription of pharmaceuticals across our catchment differs depending on where we are. Can we learn from this? Can we adjust the way we prescribe pharmaceuticals? We have to look at hospitals. Hospitals are hotspots for antimicrobial agents as well as resistance. Most of them don't have any treatment, on-site treatment required, something to look at. We also look at source solutions, interventions to, for example, high level of pharmaceuticals usage for introducing green interventions, social prescribing. So instead of prescribing a pill, for example, mild mental health problems, we might be looking into some green prescribing. But also we need to look at ourselves. So many of us are not aware of the fact that pharmaceuticals are causing huge problem in the environment. Many of us dispose pharmaceuticals down the drain. We see this all the time. On the slide, you see carbamazepine, this kind of big, dark column, was disposed on Sunday one day. A few hundred pills of this went down the drain by someone in our catchment. We need to stop this because we can see some acute intoxication happening in the receiving environment. And of course, we need to look at occupational exposure. So we do get exposed. Very often this exposure remains unnoticed. So just to summarize, we need to look at development of better tools. We are getting there, but also with better tools, we have more data. We need to know how to interrogate data. So it's fit for purpose and it can feed into the regulatory process. And we need to think about fit for purpose interventions based on evidence that we capture via our One Health thinking. Thank you.
Okay, I move on with advanced methods. Next slide, yes. So there is quite an evolution of analytical capabilities for especially organic chemicals during the last 50 years. So we have now often even high resolution mass spectrometry. We have a lot of better chromatographic resolution. We have high sensitivity. So we go to picogram per liter, we can detect today. And this is all because of the good data processing, where we have good computational tools, databases, together with the better instrumentation. And so you see here, we can now cover really compounds with low polarity to up to high polarity, and with low molecular mass to high molecular mass, which really covers PFAS, it covers PAHs and many more compounds. Next slide, please. Here I like to show you very shortly how we use the high resolution mass spectrometry to really do a target, suspect and non-target screening. So all begins with the sampling on the left. So of course you have to design your study very properly. So to think about where you want to sample, when, how much sample, and so on. And then you do the analysis with the mentioned methods. So chromatography with coupled to mass spectrometry, and with the high resolution, we have also high resolution mass spectrometry. We have full scan always data, so we have all masses at the same time, and we can store those. And then years later, we can go back to these chromatograms and check, for example, if you find a novel compound, whether this was already years ago in the sample, in these stored digital samples. Now, if you have all this analysis, then we have a lot of data, a lot of many peaks, gigabyte, and we have to do proper processing. We have to subtract blinds, we have to do replicate filtration, we have to align the retention time, and so on, so that we have really nice data. And this you can do often with targets, which we use to optimize all these parameters for the processing steps. And then we have all these data, and we have to prioritize which we really identify. So we can, it depends very much on the research question. It might be that we look at the time trend, or at the spatial trend, or at before and after a certain treatment. And then we finally identify certain compounds, novel contaminants, like the PFAS have identified in recent years, using suspect lists, so of expected compounds, or even without prior information, using all this information in the data, using spectral library and other computational tools. But this is often still time consuming, and at the end it's good to have a reference compounds for confirmation. Next slide. With that, we can really cover now in one run hundreds of targets, then also thousands of expected compounds, which we expect because they are used, for example, in large amounts, and then we can screen for the exact mass, and then all remaining compounds which we prioritize with the tools which I mentioned. Next slide. Now I like to show you examples where we have successfully applied these tools. So one is at the Rhine monitoring station in Basel, where each day is a daily screening done with LC coupled to high-resolution mass spectrometry. At the Rhine monitoring station, about 50% of the water, river water from Switzerland is discharged to Germany. So it's a very important point. And they had done this time trend analysis, and they looked at intense peaks. And here on the right, you see such peaks which have identified because of all these non-target information. For example, a precursor of a drug which has been synthesized in a certain industry and was obviously produced in batches, but in quite high amounts discharged then to the river water. And in this way, the colleagues at the Rhine monitoring station, they can try to identify source track and then to speak with the industry, and finally then mitigation measures can be introduced. So this is quite an improvement then of water quality. Next slide. And the other example is how we deal with micropollutant in wastewater treatment in Switzerland. So we have introduced a new regulation in 2016 already, that 80% of micropollutants should be eliminated in wastewater treatment using then advanced technology. And with that, in the next years, already about 20 plants have been upgraded, but more plants to come, up to 120 of the 700 treatment plants in Switzerland, to then really treat 50 to 60% of Swiss wastewater. And this costs about $10 per inhabitants per year, and the population decided they want to invest this money. Next slide. And here one result. So as technologies is in place are ozonation and activated carbon treatment. So they're really established and now in full scan in many treatment plants. And of course, we do a lot of target analysis. We have also identified some indicator compounds which are used to check this 80% elimination. But then we look also further with the high resolution mass spectrometry. And here you see such a clustering of all these signals from the influence after biology, after ozonation in this case, and after sand filtration. And then we can cluster, and you see, we can really see how many of all these signals are really eliminated already in activated sludge, which are produced in ozonation but degraded in the post-treatment, and which are really persist, also produced in ozonation and persist. And of course, these are the ones we have then to identify. I hope I could show you with these examples how powerful mass spectrometry, especially high resolution mass spectrometry, is to identify more compounds and have also better process understanding. And then with that, I give to the next.
All right, well, I'm very happy to present today on advanced methods for emerging contaminants in drinking water and also what we can do about them. There are things we can do about these things now. Next slide. So when I think about the important emerging contaminants in water, these are the things I think about. We have 6-ppd quinone. This is a brand new contaminant that researchers at the University of Washington discovered. They're killing the coho salmon in the northwest of the US. And it's an oxidation product of a tire wear contaminant, 6-ppd, that's put into tires on purpose to help extend the life of our tires, but it's getting into our creeks and rivers and hurting the coho salmon. So very important. We have PFAS that was mentioned earlier, very important. And you might know that EPA has just announced earlier this year they're going to regulate 6 of those PFAS in drinking water. So more to come on those. We have disinfection byproducts, DBPs, which is a lot of what I work with. And these are not your traditional contaminants that are manufactured by industry. These are chemicals that are formed during drinking water treatment. So when we use something like chlorine to disinfect our water, chlorine can also react with natural organic matter and other things in the water to form these byproducts. Then we have pharmaceuticals that we're concerned about, microplastics. Microplastics are everywhere now. We have emerging flame retardants. So these are newer ones that the industry is moving toward, away from the brominated ones to these newer ones. We have sunscreen chemicals. We call these UV filters. Some of those are bioaccumulative, so they're important. And then finally, algal toxins. Algal toxins are completely natural. They're not man-made, but we have all these harmful algal blooms that are increasing around the world and producing these toxins. So we need to be concerned about them as well. And most of these are a concern for drinking water and could be a concern for human health. Next slide. What's the next wave of emerging contaminants in drinking water? I would list first those ultra short chain PFAS. This would include things like trifluoroacetic acid, which has 2 carbons in its structure. Mostly we've been focusing on higher molecular weight, longer carbon chain PFAS, the legacy ones. But this trifluoroacetic acid can be found at levels 1,000 times higher than all those other PFAS. So part per billion levels instead of low part per trillion levels. So really important. We have higher molecular weight DBPs. Those that have more than 2 carbons are becoming important. One of those groups are these halocyclopentadiene DBPs that we discovered in my group about 2 years ago. They have 5 carbons in their structure, and one of those is now the most toxic of all DBPs. And of course, none of these are regulated in drinking water. Also, chemicals that are important for potable reuse are really important. So it was mentioned earlier, I think Fernando mentioned earlier a little bit about potable reuse. So potable reuse is turning wastewater into drinking water. And that's because we have a lot of water scarcity in the US and also around the world. And what happens is wastewater treatment can remove a lot of contaminants, but not everything. So some chemicals will break through. And then at potable reuse treatment, some of those can even break through the membranes and still remain in the water. And then also some of those contaminants can react with chlorine that's used to clean the membranes, RO membranes, things like this. So we need to think about those chemicals that are important for potable reuse. As our states in the US, a lot of the Western states move more in that direction of using wastewater for drinking water. And then finally, unknown compounds that drive the toxicity. We need to always be on the look for compounds that are causing new toxic effects that we're not aware of. We don't know what they are yet. Next slide. So we have emerging technologies. Next click. We have total organic fluorine. This is something we're doing in my group, and also other groups are using it now. It gives a more complete picture of PFAS. And this is not mass spectrometry. This is using combustion ion chromatography for this. So what we do is we extract the organic fluorine, the PFAS, out of the water using either activated carbon or the solid phase extraction cartridges. Then we combust either the extract from the SPE cartridges or those carbons that absorbed all the PFAS, combust them in a combustion furnace. So we're turning the organic fluorine into inorganic fluoride is what we're doing. And that fluoride then we can measure with ion chromatography. And this method will capture the known and the unknown PFAS that we don't even know what it is yet and can't measure it. Next click. Another emerging technology is GC-GC mass spectrometry, so two-dimensional GC, and this includes two different types of GC columns, so you can better pull apart, especially for highly complex samples. But we found even for drinking water, this helps pull apart things that are co-eluting that we might not be able to identify otherwise. Next click. And then also we have something called vacuum-assisted sorbent extraction, VASE. This enhances the recovery of volatile and semi-volatile analytes and can leave a complex matrix behind. I'm showing a little schematic here for drinking water where we're pulling out the DBPs of this volatile and semi-volatile DBPs. So the vacuum is helping to extract them into the headspace. They go on that green color sorbent pin that then goes into a GC mass spectrometer. And it's like an exhaustive extraction, much better than SPME, if you know SPME. And also it gets really low part per trillion level detection limits. And then we've tried this on a complex matrix like urine, and we can even measure those DBPs at low levels in urine, leaving that complex matrix behind of the urine where it doesn't gunk up your instrument. Next click. GC high resolution mass spectrometry. I want to give a shout out to this. Juliane covered this a little bit. This gives us molecular formula information for unknown volatile and semi-volatile contaminants like DBPs and also like the newer volatile PFAS. Next slide. And it's important to understand what contaminants drive the toxicity. So 2 years ago, we published this forcing factor study where we measured 72 DBPs in drinking waters from around the country in the US. And then Michael Pleva from the University of Illinois measured the toxicity, the cytotoxicity of those waters. And what we found was that haloacetonitrile, which are unregulated currently, are important toxicity drivers in US drinking water, much more important drivers than the DBPs that are currently regulated. And you see a strong correlation there between the concentration of those and the cytotoxicity. Also, we found that iodine-containing DBPs were important drivers as well. Next slide. So what can we do about this? There are ways that we can make drinking water safer now. We don't have to wait 10 or 20 years for new technologies. We have some good technologies now even. My favorite one is GAC with a low dose of chlorine. And GAC is granular activated carbon. So think of like a giant Brita filter, if you will. This is used in some full-scale treatment plants in the US and in some other countries, but it's not used at a wide scale yet. This can help lower DBP formation, and the DB in the GAC would also help to remove other contaminants like PFAS and things we don't even know yet, things we might identify next year. Think of it like a sponge that can sorb out all those other contaminants. And also, Juliane mentioned ozone for wastewater treatment is also a good disinfectant for drinking water treatment and can reduce levels of DBPs. We have UV disinfection just with light, followed by a low dose of chlorine. That's also a great alternative, and chlorine dioxide as well. And then we have ion exchange resins that can remove PFAS and also reduce bromide and iodide to lower the toxic iodinated and brominated DBPs. So these are all ways we can use now, things we can do now to make drinking water safer. And that's all I have for you today. Thank you.
All right. Hello, everyone. Thank you very much for having me in this presentation today. Very excited. Mark Ralph, I'm the president and CEO of Axine Water Technologies. And today we're going to talk a little bit about contaminant destruction. So what we do know is that contaminants are coming into our drinking water from a variety of different sources. We could have active pharmaceutical ingredients, which were previously mentioned, various industrial chemicals and solvents, and the one that's probably a little more, getting a little more attention today, is really per and polyfluoroalkyl substances, or PFAS. And these substances are coming from a variety of different sources. This could be runoff from landfills. It could be direct discharge from industrial manufacturing plants, also runoff from fertilizer plants, etc. What we do know is that these chemicals are making it into the environment, and they are leading to serious health issues in both animals and humans. Next slide, please. So the customers that Axine has have several different concerns on their mind. right? Some are very concerned about meeting state and federal maximum concentration levels associated with various contaminants. These could include PFAS or pharmaceuticals in particular jurisdictions. It could be human and animal health issues, as I mentioned a little bit earlier. Civil and criminal lawsuits, of course, you see this from large PFAS producers such as 3M, Chemours, et cetera, that are faced with civil lawsuits right now for cleanup. And then there's also the corporate and societal ESG expectations. I think many companies, especially many larger companies, have ESG goals as part of their corporate mandates. And these are looking to be achieved, and water quality is certainly an area that is very important within these expectations. With this being said, we need to come up with a solution now to address these contaminants that are making into our drinking water. Next slide, please. What Axine proposes is using a proprietary technology called electrochemical oxidation, where you are breaking down active pharmaceutical ingredients, solvents, other organics, PFAS, into their natural stable elemental gases. And these could be emitted off as hydrogen, oxygen, nitrogen, carbon dioxide, or in our case, hydrated fluoride ions. Basically, electricity is being applied to advanced catalysts to trigger direct and indirect oxidation mechanisms. These break down any contaminant or organic contaminant that is contained within the water, giving a non-selective oxidation approach. It doesn't require any hazardous chemicals, such as the addition of ozone or peroxides. Everything is done through the application of electricity across these electrodes coated with catalysts. And there's also no solid or liquid waste being generated. Next slide, please. And what we basically have, we designed this technology into treatment units. And this is an example of a 40-foot shipping container that we deployed to some of our customer sites for treating these various organic contaminants. And what you can see is that a typical unit like this, when combined with various concentration technologies such as foam fractionation or ion exchange resin, regenerant from ion exchange resin, RO, that when using these concentration technologies, we can treat upwards of 500,000 gallons of wastewater per day for these organic contaminants. We can incorporate within our containers pre- and post-treatment options such as pH adjustment or the addition of electrolytes as necessary. We have sensors equipped throughout all of our systems, allowing for 24/7 remote monitoring, and all of the data that is being collected is being used for our in-house artificial intelligence machine learning development. So there is a certain amount of remote control that we have right now, but the long-term result is that we want our systems to be run completely by computers and by the artificial intelligence perspective. With that being said, I think that brings me to my last slide. Thank you very much. I'm looking forward to participating in this discussion now.
All right. So with that, I'd like to thank the panel. It was a very interesting discussion, and I'll turn it over now to Adelina for the introduction of the next panel.